Resilience has been debated by a lot of academics in terms of a definition, but a simple and very serviceable definition for resilience is the ability to bounce back or get restored under great stresses, and also to adapt to changing conditions. This was actually the definition of resilience that was offered by the White House in 2011. How can you make infrastructure more resilient against the effects of, let's say, earthquakes as a natural hazard? And one of the things that earthquakes do is they will have a tremendous effect on geographically distributed infrastructure. Well, let's just take water supply as an example. During the 1994 Northridge earthquake in Los Angeles, there was a complete shutdown in the San Fernando Valley of the water supply of Los Angeles. It was lost because there were some areas of large ground deformation caused by soil liquefaction and other reasons that led to damaging pipelines. The fate of a pipeline is the fate of the ground. So if the ground fails, very often the pipeline is put to undue stress and causes failure in the pipeline. And once you fail a pipeline, there's no water available at other locations because the water is lost. And as a result, there was a tremendous loss of water in Los Angeles. One of the ways in which you can improve the performance of these kinds of systems is to create pipelines that will adjust to the ground movements. So a pipeline can be made relatively malleable, or it can be made flexible by a number of ways. You can put special joints in which allow the pipelines to rotate more and to pull out or compress, because there's a little bit of space in each of these joints that allow for axial compression and axial tension depending on which way the ground is moving where your pipeline is located. There's also pipeline new material. You can put in polyvinyl chlorides, you can put in high-density polyethylenes. These allow for ductility. The pipeline barrel can stretch in addition to having deformation capacities at the joints. And that allows for some ground deformation to occur. And then there are polymer lining systems. Many pipelines need to be restored. They need to be rehabilitated because they're older. It's not uncommon to go out in Los Angeles and dig around and find a pipeline that was built 100 years ago. It's certainly not uncommon to do this in New York City and many parts of the United States. These are old cast iron water mains, for example, that are very vulnerable because they're brittle to ground deformation. And so it is possible to line these pipelines in situ. That is, you don't have to dig up the ground. You can just dig a launching pit and a receiving pit, and you line with a reinforced polymer composite the inside of these brittle pipelines, and you make them malleable, you make them movable. They can now accommodate ground deformation. When an earthquake occurs, the damage scenario that you use in a model is probably not going to occur. It's probably going to be something different. But if you train an organization to look at the response of a system from several different earthquakes, and therefore be aware of the different combinations of ground deformation that can occur, then you really train them to be resilient. Dwight Eisenhower used to say that when the battle began, the battle plan was useless, but the battle planning was indispensable. So this ability to change, to modify, to adapt to new situations is a tremendous important part of resilience of institutions, of resilience of people, the people who operate the water supply.